Welcome to AI Paper Podcast. We got a really exciting paper today, one that's making some serious waves.
Yeah, this one's pretty impressive. It's called DeepSeek-Prover-V2, Advancing Formal Mathematical Reasoning via Reinforcement Learning for Subgoal Decomposition. It's from the folks at DeepSeek AI.
And the results are, well, kind of staggering. They're reporting an 88.9% pass rate on many F2F tests. That benchmark is notoriously difficult.
It really is. And they also solved 49 problems on Putnam Bench. That's a significant jump in capability for neural theorem proving.
Absolutely. It feels like we're seeing AI start to genuinely grasp the rigorous logic needed for formal math.
And this paper, it isn't just throwing numbers at us, it dives deep into how they got there. They're using a really interesting mix of reinforcement learning and this idea of breaking proofs down. Subgoal decomposition.
Right, decomposing proofs into smaller, more manageable steps. Plus, they have this clever way of generating training data, something about blending informal thinking with formal rules.
Exactly. It combines that sort of human-like intuition with the strict formal code that proof assistants like Lean-4 demand.
So for you AI researchers, ML engineers out there, wanting the absolute latest on automated reasoning, this is definitely one to unpack.
Definitely. Let's give you that quick summary first for the short form edit. So DeepSeek-Prover-V2 is this new open source model for formal theorem proving in Lean-4.
And it's hitting state-of-the-art results. 88.9% on many F2F tests, 49 problems cracked on Putnam Bench. Big numbers.
And the breakthrough comes from this novel approach. They use DeepSeek V3, their big language model, to handle subgoal decomposition, and then they combine that with reinforcement learning.
Creating a single model that can handle both informal reasoning and formal proof generation.
Right. And a key innovation is this cold start training procedure. They use recursively solved subgoals and the chain of thought reasoning from DeepSeek V3.
Which creates this unique training data, ultimately leading to these big advances in neural theorem proving. That's the gist, right?
That's the core of it. It's about the techniques as much as the results.
Okay, great. So let's dive deeper. Maybe kick things off with the basic challenge. Why is getting AI to do formal theorem proving so much harder than, say, just solving math problems written in natural language?
That's a really fundamental question. See, when we humans solve math problems, informally we use intuition, maybe draw pictures. Sometimes we approximate or, make leaps of faith that feel right.
A bit of hand-waving involved sometimes.
Exactly. But formal theorem proving, especially within systems like Lean, is brutally strict. Every single step, every logical connection has to be explicitly stated and, crucially, verifiable by the system's rules.
No room for, trust me, this bit's obvious.
None whatsoever. You have to formally prove why it's obvious, step by painstaking step. There's zero ambiguity allowed.
It's like the difference between explaining an idea to a friend versus writing a legal contract where every word matters.
That's a great analogy. An LLM might be fantastic at understanding the meaning of a math problem stated in English. It might even generate a plausible-sounding solution. But translating that into a sequence of commands that a formal system like Lean accepts as logically sound, that's a whole other level of difficulty. It demands absolute precision.
Okay, so that sets the stage. Now, the paper talks a lot about subgoal decomposition. What does that actually mean here, and why is it such a key strategy?
Right, so think about how a human mathematician tackles a really complex proof. They almost never try to solve the whole thing in one go.
No, you'd get lost immediately.
Precisely. Instead, they identify smaller, intermediate results, little stepping stones. These are lemmas, or what the paper calls subgoals. They prove each of these smaller pieces first.
And once you've proved those lemmas,
they become solid ground. Proven facts you can then use as building blocks to construct the proof for the main, bigger theorem. That's subgoal decomposition in a nutshell. Breaking a large, intimidating proof into a series of smaller, logically contained steps.
So DeepSeek-Prover-V2 is basically learning to mimic that human strategy. Find the lemmas, prove the lemmas, then assemble the final proof.
Essentially, yes. It's learning to strategically break down the mountain into smaller, more climbable hills. It avoids trying to make one giant leap.
They also mentioned something called the draft, sketch, and prove framework. Is that related?
It is related, yeah. DSP is a known approach where an AI might first generate a sort of natural language plan, a sketch, and then try to formalize it. Subgoal decomposition fits right into that idea of breaking down the proof effort.
Okay.
And it also connects really nicely to ideas from hierarchical reinforcement learning, where you teach an agent to solve a complex task by breaking into simpler subtasks.
Right, like learning to make coffee involves subtasks.
Yeah.
Get beans, grind beans, brew, etc.
Exactly the same principle. Each subgoal in theorem-proving is like one of those steps. It's typically an intermediate proposition, a statement that needs proving on its own.
So in the lean code, what would a subgoal look like? Like a function call that needs implementing?
More like a specific logical statement within the proof environment. Often it's introduced with a command like have, followed by the proposition, and then its own little proof block. It's essentially asserting, I need to prove this intermediate fact first.
Okay, got it. So creating these little self-contained proof islands, what are the big advantages of making the AI work this way?
Several big wins. First, modularity. Tackling smaller proofs is just easier, less complex search space for each one. Second, you get reusability. A proven lemma might be useful elsewhere, maybe even in a different theorem entirely.
Like building a library of useful math facts.
Kind of, yeah. And third, it dramatically improves the efficiency of the proof search. The AI isn't blindly searching everywhere, it's focused on these specific, smaller targets. The paper really emphasizes that DeepSeek-Prover-V2 was engineered specifically to be good at this, at identifying and solving these subgoals.
Let's switch gears to the data side. This cold start data collection process sounds really interesting. How did they actually create the initial training fuel for this proofer?
Yeah, this is one of the most innovative parts, I think. They built this pipeline for what they call recursive theorem proving. It starts with their big model, DeepSeek V3.
Okay.
They give it a theorem and ask it to generate two things. First, a high-level proof sketch, like in natural language, the intuitive plan.
The human-like explanation.
Exactly. And second, it formalizes that plan into Lean 4 code, but crucially, it inserts sorry placeholders for the parts it hasn't fully proven yet. These sorries mark the subgoals.
So it generates the outline, both informally and formally, but leaves these to-do markers for the actual tricky bits, the subgoals.
Precisely. And here's where the recursive part and a bit of clever efficiency comes in. For each of those sorry subgoals, they don't use the giant DeepSeek V3 again. Instead, they use a smaller, much cheaper 7 billion parameter model to actually find the formal proof for just that specific subgoal.
Okay. So offload the detailed grunt work to a more specialized, smaller model. That saves a ton of compute, I bet.
Huge savings. And they wrap this in a curriculum learning framework, too. They use these successfully decomposed subgoals to generate new related theorems, gradually increasing the difficulty.
So the system is kind of teaching itself by generating its own practice problems based on what it just figured out.
You got it. It helps guide the learning process. But here's the absolute key step. When that smaller model does successfully prove a subgoal, they take that complete formal step-by-step proof and they pair it directly with the original natural language chain of thought reasoning that DeepSeek V3 generated for that specific subgoal.
Okay, wait, so they're linking the informal explanation directly to the formal code that proves it.
Exactly. That paired data, the informal why linked to the formal how, that's the cold start reasoning data. It's incredibly powerful because it explicitly teaches the model how to connect intuitive reasoning paths with the rigorous formal steps needed to make Lean happy.
That makes so much sense. You're training it on the translation process itself. How do they then use reinforcement learning on top of this?
So once the model gets this initial supervised fine-tuning on the cold start data, they move to an RL phase to sharpen its proof-generating skills even further.
And the reward is just, did the proof work?
Primarily, yes. The main reward signal is just a binary yes-no. Did the generated Lean code verify correctly or not? Simple, but a very clear signal in this domain.
It seems straightforward. Did they run into any issues with just using that binary reward?
They did notice one thing. Sometimes the model would generate a perfectly valid proof, but it wouldn't actually follow the subgoal structure suggested by the initial chain of thought reasoning. It might find a clever shortcut, but ignore the lemmas it was supposed to prove along the way.
So it got the right answer, but didn't show its work according to the plan.
Pretty much. So to fix that, especially early in the RL training, they added what they call a consistency reward. This nudges the model to actually generate proofs that align structurally with the chain of thought, encouraging it to use those have statements for the decomposed lemmas.
So it's rewarded for being both correct and following the intended logical path.
Exactly. And they found this consistency reward really helped improve performance, especially on the harder, more complex theorems where sticking to a structured plan is crucial.
Okay, interesting. Now, the paper mentions two distinct training modes or operating modes, a non-chain of thought, non-COTI mode, and a chain of thought COTI mode. Can you break down the difference?
Sure. These are basically two different ways the model can generate a proof, and they're controlled by how you prompt it. The non-COTI mode is all about speed and efficiency. It aims to just output the final, concise, lean-proof code directly without spelling out all the intermediate reasoning steps.
Just the answer, basically.
Right. Optimized for quick generation and verification, which is useful during parts of the training loop. The COTI mode, on the other hand, prioritizes transparency and, as it turns out, accuracy. It explicitly generates the step-by-step reasoning, the chain of thought, often in comments or intermediate steps before or alongside the formal lean code.
So it shows its work. More like how a human might write out a proof.
Exactly. And this COTI mode tends to perform better, especially on harder problems, even though it generates more tokens.
How did they train these different modes?
It's a bit staged. They first trained the non-code model using something called expert iteration within that curriculum learning framework we mentioned. The model tries problems, successful proofs get added back to the training data, it gets better, repeat. The speed of non-COTI helps here.
Self-improvement loop.
Right. Then in a second stage, they bring in that valuable cold start COTI data. They use this to train the COTI capabilities, and then they further refine the COTI mode using reinforcement learning. Expert iteration is used again here too. The best prover tries unsolved problems, adding successes back into the data pool.
And this was all fine-tuning on top of a massive model, right? DeepSeek V3 base 671B.
Yep, they started with that huge 671 billion parameter base model. They did supervised fine-tuning with specific learning rates, a large context window, using both the non-COTI data from expert iteration and that crucial cold start COTI data.
Okay, and for the RL part, they mentioned using GRPO instead of PPO.
Okay.
Any reason why?
They used Group Relative Policy Optimization, GRPO. They suggest it's well suited here. A potential advantage over PPO is that GRPO doesn't need a separate critic model to estimate value. It works by sampling a group of potential proofs for a problem and optimizes the policy based on the relative success that they verify within that group.
Simpler architecture, maybe.
Potentially, yeah.
gone.
And given the clear binary reward, signal proof works or it doesn't. Maybe estimating state value with a critic is less critical than in other RL domains. They also carefully curated the problems used during RL, making sure they were hard enough to learn from, but not impossible.
Right, got to be in that sweet spot. And finally, how did they get the smaller 7B version? Was it just trained from scratch?
No, they used distillation. They took an existing 7B parameter model and fine-tuned it further using the rollout data generated during the reinforcement learning phase of the big 671B model. They also mixed in the non-Kathis data.
So the little model learns from the experience of the big model.
Kind of, yeah. They also specifically extended the context length for the 7B model during this process and applied RL techniques directly to it as well to squeeze out more performance.
Okay, that covers the how pretty thoroughly.
Yep.
Let's get to the performance, the benchmarks. Mini F2F was the big one. What were the headline results there?
Just spectacular, really. On the Mini F2F test set, the 671B model using the COTI strategy hit 82.4% accuracy with just 32 attempts per problem.
That's already state-of-the-art, right?
Yes. And when they increased the budget to 892 attempts, it climbed to 88.9%. Just massive. Even the 7B model was highly competitive, beating other open source provers.
And you saw performance scale with more compute, more attempts.
Clearly. The gap between the 7B and 671B models also widened with more samples, showing the bigger model makes better use of the extra search. And remember that Subgoal guided curriculum learning. Using that, they hit 90.2% on the Mini F2F valid set. Really shows this approach works.
Did they break down which types of math problems it was good at? Like Olympiad problems versus standard competition math?
They did. Table 2 in the paper shows IMO, AIM, AMC, and math problems. On AIM problems, which are quite challenging high school level competition problems, the 671B model formally solves 6 out of 15.
How does that compare to just, like, solving them informally?
Well, their base DeepSeek V3 model could solve 8 out of 15 informally. So 6 formal proofs versus 8 informal solutions. That gap between intuitive understanding and rigorous proof is definitely narrowing.
That's a really concrete example of progress. progress. And the COT versus non-COT comparison.
COT consistently outperformed non-COT significantly, reinforcing the idea that explicitly reasoning through the steps helps, even in this formal setting. Though interestingly, they noted the larger non-COT model sometimes seemed to embed implicit reasoning within its proof code, which is kind of fascinating.
Huh. Okay, what about harder stuff? Undergraduate level, ProofNet and the infamous Putnam.
Yeah, they tested on those too. On ProofNet, COT again showed a clear advantage over non-COT, suggesting good generalizations since the training was mostly high school level. And on Putnam Bench, which is known for being incredibly difficult, even for top human math students.
Yeah, Putnam problems are brutal.
Absolutely. The 671B model managed to solve 49 problems. That's a really strong showing and way better than its non-COT version.
49 Putnam problems formally proven by AI. Wow. Any surprises there?
Actually, yes. Kind of a weird result. The smaller 7B non-COT model solved 13 Putnam problems that the larger 671B model didn't solve.
Wait, the smaller model solved unique hard problems. How?
They looked into it and found it seemed to learn a specific, useful reasoning pattern related to cardinal numbers, cardinal.to-nat, cardinal.nat, cast account at, that the bigger model just didn't pick up or utilize in the same way. It suggests different scales might find different niches or strategies. Really interesting.
It is fascinating. Shows there's still subtlety in how these models learn. Did they look at other areas like combinatorics?
Briefly, they tested on Combi Bench, providing the solution statement. It showed promising generalization, even though combinatorics wasn't the main training focus, which was more number theory and algebra.
Okay. And lastly, they introduced their own benchmark, Proverb Bench. Why create a new one?
Right, Proverb Bench. It has 325 problems, 15 from recent AIM exams, and 310 from textbooks. The goal was to get better evaluation across both high school and undergrad levels, filling some gaps.
Did they have to curate the AIM problems?
Yeah, they filtered out geometry, combinatorics, and counting problems from AIM because those can be tricky to formalize cleanly in systems like Lean. Focus was more on algebra and number theory.
And the results on Proverb Bench. How did DeepSeek-Prover-V2 do?
On that AIM subset within ProverBench, the 671B COP model again solved 6 out of 15 formally, mirroring the F2F AIM results and getting close to the informal baseline. Across the full ProverBench, the COP model consistently came out on top compared to baselines.
Okay, so across the board, pretty much state-of-the-art performance, especially with the Kashi reasoning.
Absolutely. It's a very convincing demonstration.
So let's try and synthesize all of this. What are the big takeaways for someone listening? What makes DeepSeek-Prover-V2 so significant?
I think there are a few key things. First, it really validates the strategy of subgoal decomposition, mimicking how humans break down proofs. Second, that novel cold start data generation process is a really big deal. Linking the informal chain of thought to the formal proof steps seems crucial for teaching these models robust reasoning.
Right, bridging that gap.
Exactly. And third, the application of reinforcement learning, especially with that consistency reward, helps refine the model to generate not just correct, but well-structured and intended proofs. The end result is state-of-the-art performance on very challenging formal math benchmarks.
It genuinely feels like they're pushing the boundary of what AI can do in terms of rigorous logical reasoning. The gap between informal problem solving and formal proof seems smaller now.
It definitely does. It's a significant step forward.
So looking ahead, what's the provocative thought here? Where does this lead and what should we be thinking about?
Well, the authors themselves say they want to scale this further, maybe eventually tackle problems at the International Mathematical Olympiad, IMO level. That's the ultimate proving ground right now.
Wow, IMO level. That would be incredible.
It would. So this work is a major milestone on that path. But beyond competitions, think about the implications. If AI can reliably reason with this level of formal rigor, imagine its potential to assist human mathematicians in discovering new proofs or verifying the correctness of extremely complex software or hardware systems.
Or even verifying scientific theories that rely on heavy mathematics.
Potentially, yes. It opens doors for AI to contribute to highly rigorous fields in ways we're only beginning to explore. So the thought to leave you with is, what happens when AI doesn't just understand language, but masters the universal language of logic and proof?
A powerful thought. And if people want to dig into the nitty-gritty,
definitely check out the paper and their open source repository. The code and methodology are available, which is fantastic for the community. It's a great chance to see exactly how they built this.
It's excellent. A really fascinating paper and a great discussion. Thanks for breaking it down.
My pleasure. It's exciting stuff.